Hi, we are here to present matching for robust facial landmark localization. My name is Jade, and this is my group,
This is Karrar.
This is Redouane.
and this is our final project for computer vision.
So we're going to start talking about this project by the history first of facial landmark localization. Uh, facial landmark localization, also known as face alignment, is used in many processes such as 3D facial reconstruction, facial recognition, and many other applications. We use this method mainly to compute the visibility and position of 2D landmarks from multi-view face images. Uh, so, uh, to provide an accurate basis for identifying a person or a face from a digital image. The earliest instances of facial recognition technology actually began in the 1960s with Woody, Helen, and also Charles. They all worked together using a book of mugshots to identify matching facial features. In the conclusion of our project, actually of this project, Woody described several difficulties such as variability in head rotation, lighting intensity, facial expression, aging, and many other factors.
All right, let's talk about the problems. In this slide, we're gonna explain the problems and actually the motivation why we attack this problem because everybody working on the images and especially the facial landmark localization, which is known as the face alignment, facing two major problems. The first one is the large variability in pose and appearance. Basically, if you go to the internet, you have like different and like million and thousands of pictures, and all of them they have different pose and like different angles. And the second problem is the existence of the collisions in real world face images. Basically, is the similarity between two pictures that should not meant to be like similar, but at a certain point it will look similar to the observer. And today, as we know, the facial alignment techniques have become incredibly more advanced. Yet many of these original difficulties still exist. This report aimed to address the two major problems, as we talked about, of the landmark localization. These being being a large variability in pose and appearance, as we talked about, and also the existence of collisions in real world face images. These collisions are miscalculated based on the light lightning exposed to the images, and thus proceeding that what it does is create the cluttering and other noise in the reproduced images. When we have more light or unwanted light for these images, basically what happened, it gives us like noise on the image, and we have to fix that to proceed with our project.
As we discussed, there are many problems with this, but the reason that we care that it's not so efficient is because improving facial recognition techniques stems from its many uses in computer vision applications such as facial reconstruction, expression recognition, and expression retargeting. As we mentioned, current methods are still far from accurate. Some of these problems are contributed by the issue of localizing facial landmark points in the real world, and as we discussed, the cluttering of images due to these occlusions. A lot of facial alignment processing is used in security cameras, and as you know, these days the iPhone uses facial recognition to unlock your phone. What we're trying to prevent is someone else unlocking your phone, or maybe a criminal being wrongly identified due to a mismatched facial recognition or facial alignment, beginning with the image processing.
Uh, the next slide, as shown, is actually the different appearance and pose. For example, for face alignment, for example, in the left picture, we use the face alignment to determine where the woman is looking. For the middle one, is used where the specific woman's face is located. And for the right picture, uh, we determine if the man in the picture is wearing sunglasses.
Current methods of facial landmark localization matching use various things such as landmark extraction and relative positioning. These usually use algorithms which aren't very accurate. The approach that we chose was more accurate, and they are a lot newer. And the one that we chose was exemplar-based graph matching, also known as EGM. EGM provides a robust framework for facial landmark localization in comparison to these conventional algorithms. It uses graphs to encode structural information and compare inexact matches to find the best possible matches among a range of data. EGM has 3 specific advantages over other methods, and these are as follows. The first is in a fine invariant shape constraint is learned online from similar exemplars to better adapt to the test face. This is, as we described earlier, if someone tilts their head, if the lighting conditions are different, this range of examples will have a better data set to pull from. The second is the optimal landmark configuration can be directly obtained, solving a graph matching problem with the learned shape constraint. So after it takes these samples, it puts them into a matrix, and instead of just a couple of parameters, it uses an entire matrix of points and chooses this and matches the graphs from different graphs based on if it exceeds a threshold or not. Lastly, the graph matching problem can be optimized efficiently by linear programming. So we used MATLAB in our project, and MATLAB runs a lot quicker when you process arrays versus when you process several lines of code.
In this slide, we're gonna talk about the bigger circle, large weight. We're gonna do a couple of steps here to get better efficiency for our product or our end result. These steps are greatly condensed actually in the example in this example. We begin to perform methods to determine efficient candidate point. Then we perform the affine invariant shape constraint to further determine optimal points. Finally, we combine these methods to choose an optimal interface for the face landmark we choose. As shown, a large circle, the larger weight for choosing that point. Smaller circle are less likely candidates. So basically, is the bigger the circle is, like it will be a good candidate for us to for the program to keep, and the smaller circle is going to be discarded from this. So it will give us better efficiency around the clutter area of the picture.
A very top level diagram of our proposed system for the EGM facial matching is shown. The approach to EGM follows a series of steps. It begins with training, next the sliding window, third ransack, fourth learning, and lastly 5 matching. To further explain these steps, the first step to EGM face alignment begins with training, in which the user trains individual landmark detectors based on SVR, a support vector regressor. Positive and negative patches are sampled from these training images manually using labeled landmarks. Next, a sliding window manner is used by detectors to produce a response map of each landmark from the test images. Then, ransack algorithms are used to search for a set of similar exemplars in the training data set to generate candidate positions for the landmarks. Usually, the top 5 peak points are chosen from the response map. Next, using exemplars produced by the ransack algorithm, a quadratic programming problem is solved to obtain a shape constraint in an adaptive method for the test face. This makes the system more robust to variations in pose and other problems that we mentioned before. Finally, the matching problem is approached by combining the candidate position and the learned shape constraints, and the optimal landmark positions are chosen.
Now we're going to talk about landmark detector training. So in this project, we have condensed the methods to the following parameters. So as you can see, we have 29 landmarks, 858 training images, 3 positive patches per image, and also 6 negative patches per image using root sift plus SVM regression, which is known as support vector regressor method. The k-set of landmark candidates and M exemplar face is aimed to find the optimal subset of candidates in 2 steps. The first step we're talking about is learning the affine invariant shape constraint from the similar examples. And the second step is about solving a graph matching problem to find the optimal candidates. The graphs are shown in picture B in green, blue, and red. These are matched to find appropriate landmarks. As you can see, the first images has the 29 landmarks, which provides the significant point which produced the consistently good results.
In this slide, we're gonna talk about the graph matching. The graph matching is showing if you look at to the right, you see the synthetic example and the test image with basically we tested 8 candidate for 4 landmark as is shown in the slide. In picture A and picture B shows the exemplar graph, and if you look at the picture C shows the correspondence matrix for matching. A global coordinate matrix is produced to perform ransack searching. After reduction of these matrices, we use the MATLAB code or MATLAB solver to find the optimal solution for the coordinate matrix. The coordinate matrix provide optimal points for the face alignment. So basically in the graph matching slide, we have the synthetic exemplar and we have A, B, and C. And we use the MATLAB solver to basically to do the ransack search, and you use the MATLAB capability to get us to this point and through the matrices. And basically the coordinate matrix provide the optimal point for the face alignment.
Just to further elaborate on this slide, the synthetic example is just to show how facial alignment and how the code works. For a person, like we showed earlier, 29 points were just a condensed version. Here we only have 8 points, and you can already see how big the matrices will be. The reason that facial alignment gets so convoluted is because of the number of points that you need, and you further condense those points to create good landmarks. The reason that EGM is so good is because it uses the graphs to match with other graphs so that your accuracy isn't just based on X, Y, and Z, it's based on a whole subset of examples. Now we'll go into evaluating the research that we've done from the project and evaluating the study that we did. Evaluating the study of face alignment that we researched, the exemplar graph-based methods have shown to be significantly better than other conventional algorithms. Whenever we did some side-by-side comparison, we've seen that the typical algorithms only approach the landmarks in one way, where our non-affine approach allows for the higher versatility of images. Like we said, you can change the range of age in the person, you can change the lighting, you can change other things. The graph matching allows MATLAB to more efficiently process these matrices also, versus the numerous lines of code that an algorithm would use. The non-affine approach, as we discussed, it allows the processing to vary with the image. So you don't just have these set parameters, you can process an image a lot more fluidly. Our study showed significant success in the landmark matching. When we ran it a couple of times, and from the report that we read, it said that it only takes 2 seconds in MATLAB to run the exemplar graph-based method versus 9 seconds using other methods. From 2 seconds to 9 seconds based on one image, you can only imagine if you were processing in real time or if you were processing a huge range of images, how much of a difference that would make. So from 2 to 9, that's over half of the processing time. As we evaluated this, we have concluded that further research into EGM for facial landmark matching would produce even more accurate results. So obviously, the more images and the better quality of images that you use for exemplars are going to create a huge difference in your results. So the more examples that you have of that face, the better the facial alignment is going to be. Finally, we have concluded that exemplar-based graph matching for facial alignment works. It does work, and it works significantly better than all other methods out there. This is due to several reasons, as we have previously discussed. These are the facial shape reinforcement due to the system training. As we said, the more images that you have to train, the better your thing is trained, the better your system is trained, the better it can match these images. Using a large sample size to allow the system to learn the affine invariant shape constraints. Once it produces these shape constraints, it can map them into the graph, and you can perform the graph matching with the positive and negative images. And finally, you can solve the linear programming based on graph matching to produce the optimal landmark configuration. So just to reiterate everything that we've said, the exemplar graph matching uses a training method. It can pull from online, it can pull from different sources to train your system to have a better result. And once your system is trained, you can use that to perform the algorithms. Instead of just taking an algorithm to it, you do a bunch of processing before, create the response map, the sliding window, use the detectors and the SVM training, and then perform the algorithm using ransack to produce candidate points and use the similar exemplars. So you take a large range of these candidate points, and then you perform the processing and use the shape constraints to finally produce an inference and finally find your points that you use for the facial alignment. And that is our conclusion. Thank you.
Thank you so much.
Thank you so much.